Thank you all for coming to this talk. Um, First of all, I want a little caveat. This is work I've done with Stuart Robbins, but not quite everything I'm going to say has been fully vetted by him yet. So feel free to give him all the credit, but save all the blame for me. We're going to talk about cratering statistics, the theory, and some significant corrections to existing methods. So first of all, shout out to Don Davis for making lots of wonderful public domain images. And then a trigger warning. In this talk, there will be destruction. I am coming for the beloved tools of cratering statistics. Nothing will be spared. The Poisson timing method, square root of n error bars, the cumulative plot, least squares slopes, MLE slopes, production functions themselves. They will all be exposed as useful approximations that made plenty of sense when we had less computational power. We begin with the cumulative plot. For each crater, it plots the cumulative count, the number of craters of at least its diameter per unit area, as standardized by Arvidsson et al. 1979, the Crater Analysis Techniques Working Group. This is the classic plot. You know it well, but it holds secrets. Today, I will reveal a few. You might have heard these error bars are wrong, but we don't even know what the right ones are. I think this is the answer, but we'll get there. For now, let's get rid of them and ask a harder question. What are the error bars on the slope? We can find the slope with a simple least squares fit. For the slope error bars, let's try brute force. We generated these 100 craters randomly from a production function with a slope of -2. We can do it again. This time it's steeper than the model slope. Now let's do it 100 times, 200 times, 300, 400, 500. As you can see, we're starting to build up statistics. Now let's go to 1,000 and watch it converge to the model slope of -2. Now let's do 10,000. Wait, it's not converging. It's getting further away. Surely it will converge to -2 by 100,000, but it doesn't. There's a bias towards shallow slopes. And it's not just with n equals 100 craters either. We did this experiment at 30 n values from 10 to 7,943. Each middle dot shows the peak of the distribution of results, and the upper and lower ones are error bars. We show the full distributions at n's of 100 and 1,000 as examples, and each n has its own results distribution. This result should trouble us. The slope bias is real. Yes, it fades at high n, but some n's aren't high. Most NPF, Neuquén production function calibration terrains, had n under 100, for instance. We need to figure out what's happening. As we tried to explain this result, we figured out some things. Let's start with error bars. For that, we need to dig into the theory. Do not worry, there will be math. Let's count craters. There are 3 above our diameter cutoff. Now we cut our area into thirds. The average count is 1. 2, 0, 1. We observe n. It's our observed count. But n differs because of random chance. So we need the model count, that special version of n that reflects the underlying cratering rate, the n we would get if we repeated the experiment infinite times. We call it lambda. There is a mathematical law that relates lambda and n. As long as the craters are random independent events, it should govern cratering statistics. The Poisson distribution. If we know lambda, we can find the probabilities of each possible value of n. At lambda of 3, there is a 22.4% chance that n will be 3. And if we know n, we can find the relative probability density function, or PDF. We're going to use that word a lot, of lambda. Each relative PDF needs to be normalized so that it integrates to 1. To do that, let's recognize this equation as the PDF of a well-known distribution, the gamma distribution. And here, x, which is the variable, is lambda. Alpha, the gamma distribution parameter, is n plus 1. And beta is 1. So it's actually already normalized. The only change is to swap the factorial for the gamma function. And the gamma function is a continuous extrapolation of the factorial where gamma of n plus 1 is n factorial. Here's the lambda PDF of this image, where n is 3. At n of 3, the lambda PDF reads 22.4%. Robbins et al., 2018, challenged the focus on Poisson statistics, pointing out that other sources of error can exceed Poisson counting uncertainty. Diameter measurements, for instance, are not perfect. This one isn't quite circular. There will be some human error. They used diameter uncertainty kernels to build up the curves, and they argued that we do not yet understand the sources well enough, so we should just quantify error with the frequentist bootstrap, and they do have a point. To use the gamma distribution, we need to understand it much, much better. So let's do that. The Crater Analysis Techniques Working Group, Arvidsson et al., 1979, did not say it explicitly, but they actually used an approximation of the gamma distribution. You see, the central limit theorem says that the gamma distribution approaches a normal distribution with a standard deviation of the square root of n as n approaches infinity. And it's a good approximation at 100. As n drops, differences grow stronger and stronger and stronger. By n of 1, it's a poor approximation, and it cannot cover 0 crater observations at all. Michael et al., 2016, took Poisson statistics much further with an explosive claim. Diameters do not matter at all when it comes to finding the age. You can calculate an age PDF directly from just the total n. They started with a Poisson distribution, applied it to infinitesimal diameter intervals, combined the intervals in a mathematical proof that showed that the diameters of individual craters do not matter if you are looking for an age. And to find the age PDF, you just apply the production and chronology functions to the Poisson distribution of the raw total n. There were some skeptics. Originally, I was one of them. And under the Michael et al. 2016 Poisson timing approach, you do not fit isochrons anymore. And you can produce age PDFs from very low n, even 0. Here's Michael et al. 2022, for example, doing just that with ages from a count of 0. And here's the thing, they're right. With synthetic modeling, we confirm it. To do this, we broke the production function into small diameter increments, applying the Poisson distribution to each increment. We modeled 1 million synthetics for lambdas of 2.55 and 20. And the distribution of total n exactly matched the Poisson distribution, even though we applied it separately at different diameters. Michael et al. 2016 proposed expressing the PDF as a median with percentile-based error bars that approximate the error bars of a normal distribution. Here's what their median-based method looks like. For n of 2, the median is 2.67, higher than 2. But if you want the closest thing to a normal distribution, I say just fit a normal distribution. And these are asymmetric, so let's fit an asymmetric normal distribution. I think this is what most people assume when they see a number with error bars. But we're talking about plots, log plots, so we care most about what the least squares fit assumes. Because our plots are in log space, it assumes a normal distribution in log space. So we fit a log space asymmetric normal distribution. Linear space, log space. It's the closest match. Back in linear space too. It even fits well at n of 1. The other methods do not. Even at n of 5, the median method still misleads plots. By 10, the differences start to drop away. At 100, they all fit quite closely. But the log method does break down for an n of 0, and we had to steal the median method error bar. But to really understand when to use which method, we have to talk about Bayesian statistics, which is all about how the likelihood information from your data changes your prior beliefs. For instance, you might assume this is an image of Thomas Bayes. That's your prior. But I'm going to show you some data whose likelihood will update your prior to a posterior. This image comes from Wikipedia. Here's its caption. It reduces the chance that this is Bayes. Your posterior has a much smaller chance that this could be Bayes. We've just done Bayesian statistics. The Poisson PDFs are Bayesian likelihoods. Observing n craters shifts the prior towards n. Here, the prior starts out at 1.12. We have a likelihood of 3. And that posterior gets shifted towards 3. Sometimes they combine for a new shape, but ideally our data will dominate over the prior. Michael et al. 2016 suggest a uniform age prior. To see what this means, let's look at n of 0. They say you can get a model age from an n of 0 observation, and then they went and did it in 2022. But here's the thing. Observing 0 craters shifts a non-uniform prior left. A crater count of 0 is evidence of lower lambda and age. But with a uniform age prior, the likelihood becomes the posterior. It's as if we had no prior at all. The forms of the curves are all about how they affect priors. If we start treating them as posteriors, things get weird. It's time for a thought experiment. This is the south pole of Mars. To me, its layers of dry ice are almost as beautiful as plots of crater counts. Some say the winter layer of dry ice on the south pole of Mars is transient because CO2 supposedly sublimates in the blistering heat of the Martian summer. But we know better because there are no craters. So it's 336 million years old. That's what a uniform prior gives you. Those are our assumptions. They actually do know this. They said the uniform age prior is wrong for ice. But 0 crater PDFs always shift the prior left. They're always evidence of lower age, never higher age. And that's as true on fresh crater ejecta as it is on ice. And Michael et al. 2016's uniform age prior has other problems too. For instance, let's date a lunar terrain with 10 craters larger than 1 kilometer and an area of 2,500 kilometers squared. First, we get the PDF and divide by the area. To get n of 1, the number of craters larger than 1 kilometer per unit area, we apply the Neumann production function, which I'll abbreviate as NPF. To get the age, we apply the inverse of the Neumann chronology function, NCF. Here's where you'd apply a uniform age prior. It wouldn't change the PDF. You barely notice you did it. And that's how I tricked you. I already applied a uniform prior in step 2. It was just a uniform crater count prior. And that distinction matters. A uniform age prior is not the same as a uniform crater count prior. And yes, it changes the answer. With a uniform crater count prior, we get a median age of 3.46 GA. But with a uniform age prior, we get a considerably younger median age of 3.2 GA. When we take the posterior from a uniform age prior back to lambda space, it says lambda is probably much less than 10, with a median of just 7.26. A uniform age prior is not uniform in lambda space. Subfigure O here, right there, shows that. Not in the greater than 3GA exponential part of the Neuquim chronology function. And here's the harsh truth. Posteriors are random variables. You cannot just treat them like single numbers. There is a whole branch of math devoted to dealing with random variables, to variables who are characterized by a PDF and not just a single number. And yes, this does matter for crater counting. Let's say you have 2 crater count observations, one of 3 craters and one of 7. You want to do something as simple as add them together. You can't just say 3 plus 7 is 10. Instead, it's the convolution of their PDFs. But this seems like a lot. You might not want to figure out how to do all this math. For all these methods, I wrote a Python package called Crater Data. You can get it from GitHub. When we apply a function to a posterior, we have to worry about random variable math. That's why we get a median of 3.2 GA with a uniform age prior and 3.46 with a uniform lambda prior. Here's why you cannot destroy probability. The PDF is the derivative of probability. Once you have a posterior, the integrated probability, the area under the PDF must remain the same. So when the NCF condenses a huge amount of n of 1 space into much less age space past 3 billion years ago, it pushes the PDF up so that the area under the curve remains the same. Let's look at 2 intervals. Interval 1 is the peak of the n of 1 PDF. Its PDF value is 24% higher than interval 2, but the NCF squeezes interval 2 66% more than interval 1. So interval 2 becomes the peak of the age PDF. So is a uniform prior wrong? I can't say that. I can say it's not my prior. It's time for self-reflection, because the prior is in your heart. It is what you believe, and only you can know what it is. When we do Bayesian statistics, we share our story of how the data affected us to help the reader with their journey. And that is all. I cannot tell you that a uniform age prior is wrong. I can only tell you that it is wrong for me to help you decide what is right for you. And I can tell you not to use an error bar method for your likelihood PDFs that implies they're posteriors instead of likelihoods. The median method speaks to overall probabilities. It centers the median of integrated probability, so it is more appropriate for posteriors. The log method centers what the data show. It centers our actual n, what we actually observe. So it is more appropriate for likelihoods. For the prior, use either. For the likelihood, log or something like it. And the posterior, the median. So for Poisson error bars on plots, let's use the log method. Does it fix the slope bias that sent us down this path? Asymmetric log method errors reduce the bias, but they do not eliminate it. Oh no. There is more going on, and in fact, the cumulative plot, as you have always known it, the traditional form of the cumulative plot, what Arvidsson et al. 1979 codified in the Crater Analysis Techniques Working Group, that's biased. So let's reveal the real cumulative plot. It is a step function giving the cumulative count at every log of D, sampling it at the right of each step where the craters are creates a bias towards shallower slopes. We fix this bias by sampling the plot at the middle of each step. That's the mean in log space. We put the point for the first step right at dmin because it samples the cumulative function directly. And applying the correction reduces the bias. In our carefully chosen example, it actually eliminates it. But this was a carefully chosen example. We used synthetic modeling to look at the full data set. And oh no, because for symmetric error, when we average those error bars, it's almost gone. But for asymmetric error, it's now actually biased towards steeper slopes. Are asymmetric errors wrong? Do they worsen things? No. And to see why, it's time for the real answer. The next slide is the most important slide. I'm waiting to build your anticipation. This is a cat burrito. My wife made this image. I don't have that talent. That's right. It's a burrito because here's the thing. Crater size frequency distributions are distributions. With a flat slope, that distribution has a name. It's the Pareto distribution. It gives the probability density function, the PDF of diameter, given negative cumulative plot slope alpha. And here it is. Our Pareto graphs the Pareto PDF because we all know what burritos are shaped like. That's right, logs. This Pareto is in log space. Now let me put up the axes. In log space, the Pareto PDF is a straight line on a differential plot. And differential plots show, actually, the crater SFDs PDF. That's actually what a differential plot plots. Well, technically an unnormalized PDF. The normalized PDF will be divided by its integral all the way out to infinity. Now let's derive the likelihood PDF of negative slope alpha. We start with the Pareto PDF equation. Now we express it in terms of alpha, giving us the unnormalized relative PDF of alpha from a single crater. Wait, what? The information about alpha, about negative slope from a single crater? How can we get a slope from just one point? See, we've got another piece of information, dmin. If a crater is much larger than the minimum diameter, dmin, it is evidence of a shallower slope. If it is very close to dmin, it is evidence of a steeper slope. And then we multiply together the alpha PDFs from each crater to get the combined alpha PDF from all the craters. And here's what it looks like for our example synthetic. Now let's normalize it. Solving the integral looks hard, but there's an easier way. We reformat it. And then, remember that gamma distribution equation? We convert that equation into relative probability. And we notice that they actually match. So the combined alpha likelihood PDF from all of the craters follows a gamma distribution, just like lambda and age. Figuring this out lets us dramatically simplify the math and plot the PDFs much more efficiently. And we don't have to integrate to normalize the PDF. We just use the gamma distribution PDF equation. We just plug in our values of the gamma distribution parameters to get the normalized alpha PDF. And there it is. The equation that answers the slope problem. It also makes the math of deriving the Robbins et al. 2018 solution much easier. They proposed using the maximum likelihood estimator, the alpha value where the PDF reaches its peak. And they derived the MLE by solving for where the derivative was 0. It's long, it's complicated, but we can just plug our parameter values into the theorem for the MLE of a gamma distribution. And their MLE method slashed through the distortions of plots and fitting methods, finding the slope directly from the raw diameters. For the error model, Robbins et al. 2018 went classic. They turned to the central limit theorem, approximating it as a normal distribution with square root of n error bars. And like Michael et al. 2016 did with ages, the Robbins et al. 2018 MLE slope method represented a dramatic challenge to the existing statistical order. It swept away decades of plot-based methods, replacing them with a simple equation. But how does it perform? Let's check with synthetic modeling. Now, as a reminder, these were our results for the corrected cumulative plot, where the method we expected to perform best, asymmetric errors, actually had a bias towards steeper slopes. And when we overlay the MLE results, we can see that the MLE has a stronger bias towards steeper slopes. Still pretty accurate at medium to high n, but we want to eliminate all the bias. So what is going on? When we examine the synthetic MLE results at selected n, we can see they are highly asymmetric, even though the standard deviation percentiles form almost symmetric error bars around the mean. And the alpha likelihood PDF is asymmetric too. It follows a gamma distribution, which is asymmetric. Here's the alpha likelihood PDF from our example synthetic. Its MLE, 1.95, is less than its mean, 2.05. To see why, let's plug our parameter values into the theorem for the mean of a gamma distribution and compare it to the MLE of a gamma distribution to derive the bias of the MLE compared to the mean. There you go. But to explain our synthetic results, however, we need to compare the mean of the MLE to the model alpha. Ritgard, 1990, derived this bias by a substitution and a summation of exponential distributions. But we do it much more simply, by substituting for the MLE and seeing that it follows an inverse gamma distribution. And the inverse gamma distribution has its own theorem for the mean, which gives us the mean MLE bias. Yes, it's really just n over n minus 1. So we have an analytical equation that predicts the distribution of observed MLEs given a model alpha. That actually predicts the fundamental bias that we see reflected in so many of our slope problem fitting methods. It should match our synthetic results, where the model alpha is 2. Does it? Does it match? Yes, it does. And we have derived an analytical equation that exactly predicts our synthetic MLE results. And n over n minus 1 predicts the means too. 11/10 times 2 is 2.2. 21/20 times 2 is 1.05 times 2, or 2.1. 51/50 times 2 is 1.02 times 2, or 2.04. It really is that simple and beautiful. And now the MLE isn't exactly wrong. It's reasonable to look for the best fit slope, not the mean of the PDF. What's inaccurate is to approximate its error as symmetric. But the bias does drop to just 1% by n of 101. So should we replace the MLE with a mean likelihood estimator? We could still call it MLE to confuse you. There's a better way. we can actually just use the full PDF with all the same math that we used with ages. Oh yes, that's right. We can now do full-blown Bayesian statistics on slopes with priors and all. And we can use our error bar methods too. Here, we've used the linear method to show the asymmetry. In a sense, the biased MLE results are correct, since least squares looks for the best fit slope. So the asymmetric uncertainties take us closer to the best fit slope. Closer, but not quite all the way. So let's discuss another problem with cumulative plots, one that Chapman and Hefner raised all the way back in 1969, covariance. 1967, covariance. Fitting methods assume each point is independent from all the other points, but each point in the cumulative plot depends on the point to its right. An outlier in a cumulative plot propagates to its left, creating spurious features that look statistically significant but aren't. To show you, we made 5 random synthetics with a model count of lambda equals 100 and a flat model slope of -3. Here's one, does appear featureless. 2, we thought could interpret an inflection point, but it's purely random chance. Same thing with 3, but it's random chance. 4 looks featureless again, but we can still see outliers propagating. 5 really does look like an inflection point, but all we are seeing is outliers propagating. To see how statistically significant a slope change is, we need to find the slope PDF over an interval. It's time to meet the truncated Pareto distribution and derive the relative likelihood PDF of alpha. Here, the PDF does not follow a known distribution, and it lacks a simple closed form normalization. But we can derive the PDF numerically by dividing it by its integral. Here's an example with an interval from 10 to 20 kilometers on an NPF synthetic with a total N of 1,000. And Robinson et al. 2018 approximated it with its MLE and central limit theorem symmetric error bars. We can improve this by using the full asymmetric PDF. But here there's a much bigger problem. We calculated the means of the truncated Pareto alpha likelihood PDFs of 10,000 synthetics, and their distribution does not converge to the model slope, which is -1.193. In fact, it's quite strongly biased. And the error on the slope is very wide. For our example synthetic, with an N of 567, its alpha error is plus or minus 0.212. And if the error approached alpha over square root of n, like it does for the untruncated Pareto alpha PDF, it would be just plus or minus 0.036. It's a huge error. And we're missing something here. There is something else that gives us information about the slope. And it's something quite simple. A concept that takes us back to the fundamentals of what a slope is. Rise over run. At its core, slope is the y-axis change, the rise, over the x-axis change, the run. Here's what that looks like for a cumulative plot. Even in log space, it's a very simple equation. When we simplify it a bit, the area terms cancel out, leaving us with an even simpler equation. But wait, this is just an equation for alpha. How do we get the PDF of alpha? Remember that alpha is a gamma distributed random variable. It's got a PDF. We write it this way because we've got to do random variable math. We divide the 2 lambda PDFs with the equation for random variable division. We take the log with the equation for applying a function to a random variable. And if these equations seem hard to solve, don't worry. Our Crater data code can perform these operations numerically on any random variables. This equation actually exaggerates the error. The count at d min includes the count at d max. So we break it into the change in the count and the count at Dmax. And then the count at Dmax cancels out with the denominator, leaving us with the final equation for the slope from the rise over run PDF method. The alpha PDF from rise over run is actually much more informative than the alpha PDF from the truncated Pareto method. But they both do add information, so we don't have to choose. We can combine them with Bayes' rule. When we do, the synthetic results get closer to the slope of the NPF over the interval. And why is rise over run biased at all? Why is the truncated Pareto method so biased? Because the rise over run slope is not the same thing as the slope. If we look at just the rise over run slope over this interval, it's very close to our results. It's negative 2.05, and the mean of the means of the rise over run alpha PDFs for 10,000 synthetics is just 1.206. Very close. The rise over run slope is actually the slope between the two endpoints of the interval. If the curve were fitting as a straight line, it's the same thing. The rise over run slope will match the best fit slope. But our model production function, the NPF, is slightly curved over this interval. There's a gap between the NPF and the line connecting the endpoints of the interval. Critically, that gap isn't symmetric. It's skewed toward larger diameters. So the rise over run slope does not exactly match the best fit slope. To get the best fit slope, let's break the NPF over this interval into points on a log-log plot and fit a straight line to those points with least squares. And for precision, let's use 1,000,000 points. Because the gap is skewed, the best fit line is further above the endpoint on the right than the left. Its slope is negative 1.93, which is very slightly shallower than the rise over run slope of negative 1.206. For the PDF from the truncated Pareto method, larger craters provide evidence of shallower slope. Because the gap is skewed towards larger craters, the truncated Pareto method gives us a shallower slope. To measure the slope from the truncated Pareto method very precisely, we used a massive synthetic. We generated 1 billion synthetic craters and found the truncated Pareto method slope. It's negative 0.925. Both methods provide information about the slope, so we can combine them with Bayes' rule. The truncated Pareto method is biased, but its PDF actually corrects a slight bias in the rise over run method. Sometimes you just want the count. When we calculated an example age, we assumed a perfectly accurate production function, but here's a secret. Production functions aren't perfectly accurate. This figure from Koenig, 1977, shows the NPF calibration data out to 10 kilometers. The n values, which I've put in a table here, just are not that high, especially at the lowest diameter n. That north ray count, which is what pushes it down to 20 kilometers, and then it extrapolates beyond that, down to 10, that has an n of just 49. One goal of a production function is not to measure the slope. It's to project a count at one diameter to a count at another diameter. It's a change in the count. For production functions, slopes are actually a distraction. To get the PDF of the adjustment from one diameter to another, it's just a count. Yes, slopes are a distraction. There are complexities. The areas no longer cancel out, so we work in terms of density, rho. Each density is a sum of changes over many diameter intervals. At each interval, the PDF of change in crater density uses Bayes' rule to combine the density change PDFs of each terrain covering that interval. That's the equation. To project a crater count from one diameter to another, we don't need slopes. We don't need plots. We don't need the MPF's 11th degree polynomial in log-log space. All we need for the PDF of the adjustment is the calibration data, phases rule, random variable math, and a whole lot of gamma distributions. And so we end with a unified vision. 4 ages, 4 slopes. For projecting across diameter space, we don't need plots. We don't need error bars. We don't need approximations. Pure math gives us the full Bayesian PDFs. I want you to use these methods, so I wrote a code. I call it Crater Data. It's a Python package. Go to github.com/samwbell/craterdata to download it. Start using it. Tell me what works and what doesn't. I wrote example notebooks to explain the code. For instance, here I show the one-line function that gives the age PDF, and then I break it down step by step. I tried hard to make the code simple. To divide 2 random variable objects, you just type a slash, just like for normal numbers. To make an R-plot, it's a one-line function with plenty of keyword options, of course, and you can use all those matplotlib parameters to modify these plots after the fact. Your questions will help me improve the code. Will it be that the synthetic generation function needs the production function to be in log space, and I did not make that clear? Or will you have found a bug? This is wrong, but there's no real way for you to know that. The code gives you synthetic diameters, but they don't follow the MPF. And when you do it where you're supposed to do it, with setting PF equals NPF new log log, your synthetics do follow the NPF. And now I want your questions on something else. This talk. And the math up here is just for aesthetics. I want you to have something pretty to look at when we ask questions. All right. So, do people just want to chime in if they have any questions?
Well, this is Jeff Morgenthaler here.
All right.
What happens if you don't do crater counting, but you always thought Poisson statistics was the right way to go?
So if you don't do the crater counting, but you still have Poisson statistics. So are you referring to like an example in a totally different application? Like for instance, if you are using Poisson statistics to look at like a size frequency distribution of observed bodies like comets or something like that? Is that your
Um,
question?
well, yeah, I mean, just in general, like the description of data and error bars and N and all that good, have a random sample of something, uh, not necessarily the size frequency distribution, but I was taught, perhaps erroneously, that the Poisson distribution is, one distribution to rule them all. And you're challenging that in some aspect that's specific to the crater counting stuff, and you can do your synthetics and all that. But yeah, I mean, I guess I'd need to think about the specific applications I have and how you know once n gets over 100, then the Poisson is sort of good enough. But
Yeah. So I absolutely believe this is applicable to so many other problems outside of crater counting. In fact, in doing this research, I poured through as much as I could of math literature, and it's scattered across different fields. One of the papers I cited is by a Danish insurance risk analyst. And so, there are tons of different applications. A lot of them are in finance, which is not something I want this used for. But you absolutely can use it for all sorts of other applications. I think the most applicable application is that I can think of in planetary science is distributions of observed bodies. For instance, like people use very similar methods to look at like the slope of an asteroid family's size frequency distribution or something like that. And there, the Poisson distribution, it's still the governing distribution. I don't think you were taught wrong that it is the ultimate authority behind so many different problems. I think it is true. And there's so many problems where all the same math that ultimately flows from Poisson statistics still applies. Um,
Okay, yes. So the one application that's occurring to me is some uh, uh, looking at the distribution of outbursts from comets. Okay,
mhm,
and there's uh, Jordan Steckloff thinks or would like to test the hypothesis that all of these outbursts are triggered by mass wasting events
mhm,
surface, and that's essentially the steeper the surface, the more likely, and there's a Bible distribution that describes that. Uh,
mhm.
I guess it's sort of a fancy Poisson, or it's just its own thing. Um, so, uh, yeah, so what you're saying, well, and I guess ultimately we're proposing to use the Bible distribution because that's the right thing, because then once the source function is viable, then everything follows through.
Mhm.
I'm just trying to think of some fancy way to apply things analytically if we can. But
Yeah, I mean, I think absolutely. Uh, a lot of the math I've done here, I think is applicable to a lot of problems like that. Even actually, if it doesn't start with the Poisson distribution, you know, I had to write a code that allows you to do random variable math. And I thought that the Python package must be out there. Someone else must have written something that allows you to do a lot of that. And I'm sure I didn't do it in the most perfect, efficient way. But and some of the things I looked at, like, with the slope estimation question, um, uh, I was like, someone else must have figured out there must be some math paper out there saying, the summation of the alpha likelihood distributions from a Pareto PDF follow a gamma distribution, and I couldn't find the math paper out there. So some of this may have been actually inadvertently math research that's applicable to a bunch of other problems. I want to answer some of the questions in the chat. One of the questions is, can you use the Hartman production function with the script? You can. I didn't code the Hartman production function in, but there is a module where you put in production functions, and you can just write in any kind of production function. You just need to be able to create a Python function that describes the production function. So all of the different parts of the package that are going to use a production function, you can just put that in. Dan, does that answer your question? It says yes. All right. So the next question is, has there been a shift to favoring larger diameter craters in more geologically recent years? Um, I think that actually it's the other way around, um, because of saturation. And basically, when it's geologically older, then larger diameter craters are often more important because smaller diameter craters wind up getting saturated. One of the most important applications of these slope problem methods is trying to actually measure the very subtle slope changes that can tell you that you're done with saturation. And oftentimes, this is actually the biggest source of error in the age problem. If you know exactly that you are on the production function, you're not biased by saturation, you can pick dmin exactly precisely and get that in, then the math holds. But honestly, in most real world examples, figuring out exactly where to pick that minimum diameter that is least affected by something like saturation, erosion, resolution effects, that's really hard. And it's often done by looking at very detailed slopes. But because methods have not been good enough to measure slopes over a very narrow, truncated interval, it's been harder. So one of the key applications is actually helping sort out that problem. Um, oh, next question is, there's the link to the GitHub page. And do we have any other verbal questions?
Hey, Sam. This was a really interesting talk, and your delivery was excellent. It's very engaging. And I was just wondering, when you use the crater data Python code that you've written and you have it run and it runs and it gives an age, have you compared that to like other studies using the more traditional method, like using crater stats software or something? Like what kind of differences do you see?
Yeah, so the Crater Stats software, its updated version is that Michael et al. 2016 Poisson timing approach. So those differences are going to heavily depend on a couple of things. One, it's that subtle thing about a uniform age prior versus a uniform crater count prior, which the priors are supposed to not inform the data, but actually it's sort of an informative prior that winds up biasing the results in the subtle way that I described. And it can be particularly important in ages in sort of the 3 GA range. That's going to be the biggest difference. The other difference is that my method allows for incorporation of other sources of error. So when you incorporate all other sources of error, you're going to have to wind up using the random variable math. For instance, let's say that you say age is something, or area is something you don't know exactly. For a lot of low end counts, you really don't know your area exactly. It really depends. Like, let's say you're dating a continuous ejecta blanket, and it's got 15 craters on it, and you need to figure out what the edge of your boundary is. It's not going to be super clear, and that area asymmetry is probably meaningful uncertainty. With this method, you can just treat area as a random variable, and then you can calculate that out. So I think the real advantage over that method is that you can incorporate so many other sources of error. And then at the end, if you want to work with the data, you can work with them using the random variable math. To compare it to the isochron fitting, I did run some synthetic models on that. They wind up having a bias towards older ages, heavily driven by the sampling issue with the cumulative plot, and then somewhat similar dynamics, other dynamics, because a lot of those are binned plots that people use. Those also have an older age bias for other reasons, having to do with the missing interval of skipping zero crater bins. And in particular, because a lot of them were done from cumulative, there was a trend in using the cumulative bin distribution where you would skip a pseudo bin if it had zero craters in it. And that bias wound up creating actually a pretty considerable bias because you were just like ignoring all the zeros. And when that happened, that actually wound up leading towards a bias towards older ages. And when you don't actually include error, if you just did like a simple fit, you'd wind up getting pretty considerable biases. Does that answer your question?
It does. Yeah. Thanks again.
All right. Any other questions?
All right. Well, thank you so much, Sam. It's interesting.
All right. Yeah. Thank you guys. And if anyone wants to download the code and play with it and find my mistakes before the reviewers miss them, that would be awesome. All right. Thank you all.